Hello guys, thank you so much for being with me in another machine learning tutorial video. So far we have introduced the supervised learning and introduced both types of supervised learning. In the previous video we talked about logistic regression, and we are going to extend it to neural networks. When dealing with real world problems, we usually face a problem called overfitting. In the real world, we do not have the dotted line function, which is available in the Python files, which I have prepared for you. And in solving machine learning problems, the goal is to learn this function. The orange function in the Python files is the function that we have tried to predict, so that it is very close to this dotted line function and exactly matches the data in the training set. In this example, we have used many features and the degree of this function is very high. Here it is the degree 15. This function works well for existing data in the training set, but not well for new data because our model is too complicated. This problem is too common. There are different ways to reduce this problem or even eliminate it. One of the most common ways is regularization. Pay attention that in reality we do not have the dotted line function in the Python files. If we consider a first order function to approximate this dashed line function, you can see that this function is not very good. Now if we check a function of degree 4, we can see that by adding features and raising the degree, we have been able to reduce the error and approximate the function to a good extent. In this case, the error on the training data set is very low. Now if we increase the number of features and increase the degree of this function to 15, the error on the data of the training set is very good. But in case of new data input, the model does not perform well at all. More than enough degree and complexity lead to overfitting problem. In the case where we considered the linear function, the problem was underfitting. It means that our function and the model were too simple, but this is not the main problem in the real world because this function does not perform well even on the training data set, so it is easily recognizable and it can be made more complicated by increasing the features. But in the overfitting problem, we never noticed the problem by considering the performance of the function on the data in the training set, and this is where the main problem occurs. In the Python files, I have provided you with examples in this regard. At first, I have illustrated the problem of underfitting for you. Then we have taken into account the increase in degree and features, and gradually we have reached the optimal solution. After that, with the increase of the degree and features, the problem of overfitting appears little by little. This problem also exists in finding the decision boundary. We can improve this boundary by increasing features, but if we increase these features too much, the problem of overfitting will happen. The idea of regularization is that we want to regularize. We don't want to let the model get too complicated. The reason for this complexity is that there are too many features. In mathematics, smooth functions are functions whose output value does not change much with a very small change in the input, so the function is not smooth when overfitting occurs. What causes this unsmoothness is the high coefficient of polynomials and the high slope of the function in these intervals. These coefficients are actually the same parameters of theta. If we prevent these parameters from getting too large, the function will not become rough, so the complexity will not be high, and as a result it will not lead to overfitting. To achieve this goal, we need to manipulate the cost function. For better understanding, I have also drawn the graph of coefficients of polynomial sentences in the Python files. These coefficients in this picture, picture which is available in the Python files, should be multiplied by 10 in power 10. The reason for these sharp and sudden changes of this function is the largeness of this theta. In the figure inside the Python files, the absolute value of these coefficients is drawn without considering the positive or negative sign. To prevent these coefficients from becoming too large, we consider a penalty for large coefficients. We obtain the optimal value of the parameters by minimizing the cost function. To prevent these parameters from increasing too much, we add a regularization term to the cost function. From now on, we need to minimize this new cost function. By minimizing this additional term, we prevent the parameters from becoming too large. These types of problems are called multi-objective optimization problems. It means we have more than one goal. That is, we minimize both sentences. Not only do we want the cost to be minimum, but we also want the function to be smooth. And now the preference of these goals is determined by lambda. With this lambda, it is possible to establish a balance between different goals. If the smoothness of the function is more important to us, lambda should be smaller. But if matching with the data in the training set is more important for us, it should be larger. Lambda is a positive number between 0 and positive infinite. So this lambda itself is a new hyperparameter. In this lesson, we call only theta as parameters and call the rest of arguments and parameters are hyperparameters. As we advance in machine learning, the number of these hyperparameters increases, and the more these numbers increase, the more difficult it is to find the right value for them. And this ability is acquired with experience, as the main art is to find the best value for these hyperparameters. We put the most emphasis on this case in this training course. For this reason, I emphasize that you know the logic behind ready-made codes in Python. These are theta, which corresponds to the regularization term in the cost function should be such that if the value of the parameters is high, the value of this r theta should also be high, and vice versa. Theta is a vector value including theta 0 and theta 1 and so on. There are various regularization methods to define this r theta. One method is the L2 norm, which is actually a set of squares of parameters. This function is minimized when all parameters approach to 0. Here we have also written in vector form. This sign is the vector size to the power of to another Another method is to minimize the sum of the absolute values of the parameters. That this function also minimizes if theta approaches to 0. This method is called L1 norm. Similarly, there is a hybrid method called elastic net, which adds a coefficient of L2 with a coefficient of L1. Now, what is the role of this lambda? The smaller lambda is, the less effective the regularization term is. When lambda is close to 0, although the function performs well on the training set, it is not very smooth. The larger lambda is the smoother the function becomes, but it may not perform well on the data in the training set. We have to find the right lambda by trial and error. If regularization is applied even with the same function of degree 15, we can get better results. In fact, this regularization has performed a kind of feature selection and has made the coefficient of some higher order sentences 0. This happens in the L1 norm, and this answer is called the sparse answer. While in norm L2, the value of the coefficient of these sentences becomes a very, very small, but not necessarily 0. We have drawn the contour shape of the cost function in the Python files, and we know that the optimal solution is in the center at the point 0 and 0 actually. The size of theta may be too large and the function may be too uneven. From now on, in addition to minimizing the errors, we also want to minimize the coefficients of the sentences. The red minimum shape figure actually is the point 0 and 0. At this point, the answer is very, very simple because theta 1 and theta 2 are 0 and we only have a theta 0. But this function does not work for us, and now the final optimal solution is neither the center of the blue figure nor the center of the red figure. Rather, it is at the intersection of these two figures. Actually, the answer lies on this curve. The circular figure corresponds to L2 and the angular figure corresponds to L1 norm. In norm L1, the optimal points are located either on the line axis theta 1 or on the axis theta 2. That is, in L1, the optimal points are where many parameters are 0. Now, how to use these in practice? All of these explanations are visual correspondence in the Python files. Don't be worried. But I emphasize again to pay attention as much as possible to the Python files. In these examples, I have considered L2 in the Python files because it is more common, because optimizing this function is much easier because it is a continuous and convex function. In mathematics, we do optimization by differentiation, so it is good that our regularization function is differentiable. Of course, L1 optimization is also possible, but it is a little more difficult. Okay. X theta were our predictions when we subtract y, y actually from it, we get the error vector. In linear algebra, when we transpose a vector and add it to itself, it means we raise all the elements of that vector to the second power and add them together. So now we have to optimize this function, now either through gradient descent or through advanced methods introduced in the previous session. In the implementation phase, we have already seen this code snippets, and now we want to add a regularization sentence to these. If you rewrite the formulas based on mathematical rules, if you choose the value of alpha and lambda correctly, then the product of alpha and lambda should be a small positive value. It means a number between 0 and 1. So as a result, if we subtract this number from 1, we still get a positive number smaller than 1. That is, in fact, this is the same shrinkage that you will encounter in the discussion of neural networks. We have already seen the Norman equation. Which was a closed method. Now we can do this regularization in the normal equation. According to the usual rule, we take the differential and set the result equal to 0. In the course of calculations, we must multiply lambda in the unit matrix. This final equation is also called Tikhonov's regularization. We have already seen logistic regression without regularization. We can use this regularization in this field as well. Occam's principle is one of the let me find it. Okay. Occam's principle is one of the most important principles of machine learning, and it emphasizes removing extra details and avoiding model complexity. This principle between two simple and complex models that have almost the same performance prefers the simpler model because it has better generalization capability. I have put all of these implementations in the files for you. Again, I emphasize that for the optimization stage, you can use both the famous gradient descent algorithm and the more advanced optimization methods. In cases where the gradient descent algorithm does not work well, it is better to use these methods. We already said that the fourth argument can be ignored, and in this case the algorithm will estimate it. But the point is that this estimate is both slow and not very accurate. So it is better to define it ourselves. So the result of this set talks is that you must use regularization as a standard in practical examples. I have put various examples for you in the Python files. Please read them and solve the examples. Run each cell separately and pay attention to each of them. Think about the written codes and try to understand the logic behind them. Okay, I again highly recommend you not to miss the upcoming lecture because of the very practical and important tips inside them. Have a nice day.